1, 2, 3. Okay, now it is complement. So the first one would be complement. And then instead of true and false, we go to binary system. 1 represents true, 0 represents false. So from now on, we are talking about 1 and 0s, not true and false. So complementing 0 would be 1. Complementing 1 would be 0. A, complement of A bar, would be 1 if A is 0. If and only if. I mean, if A is 0, then complementing it would be 1. And if A is 1, if A bar is 1, then it means that A was 0. So it is if and only if, two-sided induction. A bar is 0 if A is 1. You know these things. I guess we can move fast. And in digital circuit, we consider 0 as low voltage and 1 as high voltage. And we are going to build gates for these things, which we will reach later. And this would be a table showing this function. So what is the function? The function is invert. The function is inverting. What is A? A is the input. If you input 0 to this function, the result would be 1. If you input 1 to this function, the result would be 0. And the symbol for this function, which is inverting, is this symbol. We call it invert gate. So this is the gate of inversion, invert gate. So if this is A is the input, output is F, then we can say F is A bar, or invert of A. The next one is AND. When you AND two things. So F, the AND of A, so not invert was a one operand. So you get A, the result would be A bar. But for AND, we have two operands. It is a binary operation, two operands needs. So we get A and B, and when we AND it, the result would be 1 if and only if both of them would be 1. A and B. The same thing in logic. When you have two expressions, when you combine them, then the result would be true if both of them are true. If one of them would be false, then the result would be false. This is the symbol of gate AND. Gate AND. We show it like that. And we can write the expression is F equals to A dot B, or we can remove dot A, B. The logical operation of dot, which corresponds almost to multiplication in decimal multiplication, is AND. A dot B. A times B is AND. We are talking about logical operations now. This is the logical operations. Yes.
In the table, what does F mean? Is that like final?
Oh, sorry. I skipped this table. F is the function. F is the output here. And A and B are the inputs. So we are saying that, I forgot to talk about this table. We are saying that if A is 0 and B is 0, then F would be 0. ANDing A and B, if both of them are 0, would be 0. If A is 0, B is 1, again the result would be 0. If A is 1, B is 0, then again the result would be 0, because one of them is 0. But if both of them are 1, then the result would be 1. This table shows the function, the function operation. How does this function work? And it is a function of and, or. So as the name shows us, this is or. So it means that either this one, either that one, or both of them work. But if none of them is there, then it is not working. So it means that f is only 0 when both of the inputs are 0. Otherwise, it is 1. If one of the inputs are 1, then the result would be 1. And this is the table. You see, A is 0, B is 0, F is 0. But if one of them is 1, if A is 0, B 1, or A is 1, B is 0, or both of them are 1, then the result would be 1. And this is the symbol of OR gate. It is not, the AND was like this. OR is curve. This is a symbol of OR. We can, to make things similar to switches, to what you may be more familiar, we have this kind of analogy. We have A and B, which was either 1 or 0. Then you consider them as a switch. For example, look at this one. This is a switch. We have two switches. ANDing these two switches means that you put them in sequence, in serial. So look at that. If both of them are closed, both the switches are closed, then the lamp is lit, is on. Then if one of them is open, one of them or both of them, then there is no light. Okay, so this is the AND. You could represent AND in the circuits with serial connection. This is AND. And again, this something similar for the OR. You could put two switches, A and B, in parallel. If one of them is closed, then the light is on because we have a circuit here, and it will be turned on. But if both of them are open, then the light is not on. Okay, so this is a good analogy that you could use for circuits. Some of the terms that we can see in Boolean algebra. The first one, A plus 0, plus is OR, dot is AND. Remember, plus is OR, dot means AND. So this plus is the logical OR, not addition. We are not talking about addition. This is logical OR. A plus 0. To find out what would be the result, the simplest thing is A is either 1 or 0. A is either 1 or 0. 1 plus 0 is 1 plus 0 is 1. 0 plus 0 is 0. So you see, whatever A is, the result would be the same. So A plus 0 is A. Or it means that if you OR something with 0, you get the same the input, whatever you had as input. An analogy to this to the circuit would be like that. So if you have a switch, then let me raise it. So if you have an open switch, so here the light depends on A only. A plus that doesn't do anything. So it depends on A. A plus 0 is A. The same thing for whatever I write at the left-hand side, I do some kind of dual for the other part, which the plus, the OR will be AND, 1 would be 0. So look at that. A and 1 is A. whatever you AND something with 1, the result would be the same as the input. And the circuit would be like that. When you have a circuit which is closed, then the light will be on based on the A only. 1 is already 1. It is closed. So A and 1 is A. Okay. A plus 1. You are ORing something with 1. Again, I told you, A is either 0, is either 1. If it is 0, 0 plus 1 is how much? 1. Or 0 or 1 is 1. 1 plus 1, 1 is 1. So if whatever A is, the result would be 1. A plus 1 is 1. And you could write the dual like this. A and 0 would be 0. Whatever you AND, whatever you have, and you AND it with 0, the result would be 0. And the circuit would be like that because this is open. So whatever you put here, it doesn't turn on the lights, and always it is 0. A plus A or A. Again, it is A because A is either 1 or 0. 1 plus 1 is 1. 0 plus 0 is 0. So 1 plus A plus A or A is A. It is like that. So you have a switch duplicated. So if it is closed, then it is closed, and then it will turn on. If it is open, then it is open, and the light is not on. So A plus A or A is A. And again, A dot A is A also. A and A is A. The same analogy, the same. And this is a very important one. A plus A bar, it means not A plus not A is 1, and A times A not is 0. How do we show that? Okay, put either 1 or 0 for A. If A is 1, then 1 plus A bar is 0. So A plus 0 is 1. If A is 0, A bar is 1, so 0 plus 1 is 1. Here, if A is 1, A bar is 0. So A 1 times 0, 1 and 0 is 0. If A is 0, then A bar is 1. 0 times 1 is 0. A plus A bar is 1. A dot A bar is 0. And the thing that we said, that negating the negated one is the same. A bar bar doing 2 knots, not of not A is A. So remember these terms, these expressions, and then we will use them to work with our expressions, with our algebra. Well, let's see some of the rules. Actually, we talked about these two. A dot A bar, A plus A bar is 1. We call it complement. The next rule is a commutative property. It means A plus B is the same as B plus A, or A dot B is the same as B dot A. Okay, commutative property. The next one would be associative property. And when you are, you can compare it to what we have in arithmetic, in regular arithmetic. A times B times C, which we first calculate B times C, then it will be the same as if you calculate A times B first and then AND it with C. A and B and C is the same as B and C ANDed with A. And the same thing for OR. A plus B plus 3 B plus C is A plus B plus C. You know, if we put parentheses, it means that we do first that one, we first operate that one, and then go to the next one. And this one, distributive property. We are familiar with that, with this in our mathematics, but only for multiplication. For example, in regular mathematics, you say x times y plus z is equal to x times y plus x times z. This is the distributive property. Only we have multiplication toward sum, toward addition, not the vice versa. For example, in arithmetic, you cannot write this. X, look at this, look, x plus y times z. We don't have distributive property for that. It doesn't come to x plus y times x plus z. No, it is not correct. This is not correct in arithmetic. But in logic, it is correct. You see, distributive, if you AND to a OR, then it distributes to both of them. So it becomes A times B plus A times C. But, and the same for ORing and AND one. A plus BC is A plus B and with A plus C. We don't have this in arithmetic, so you might do a mistake for that one. But remember, absorption. When you AND A with AB or A plus B, this is simple. Oh no, both of them needs more explanation. The simplest way that I can explain it is using A and B is either 0, 0, 0, 1, 1, 0, 1, 1, and then I calculate that and say, okay, you see, it became A. For example, let me see this one, A times AB. A times AB. No, something is wrong here. A times AB. No, it is not correct. Something is right. A plus AB. Okay, I made it wrong. A plus AB. A plus AB, and the dual would be A times A plus B. So let me write it very good. These are very important. Absorption. A times A plus B. We are saying that this will become A. If you AND A with something that I can say in my mind that it's something is bigger, then it will become A, because AND is almost getting the smallest one. And if you OR this, then again, if you are ORing A with something smaller than that, the result would be A, because OR is doing the bigger one. Let's do the expression in different situations. A, B, and then I am calculating this one, and then I am calculating A plus B, and then the last F. This is F. I want to see what is F. So A is 0, B is 0, either one. A is 0, B is 1, A is 1, B is 0, and then both of them. We have only four situations, four alternatives. 0, 0, 0, 1, 1, 0, 1, 1. Okay. If A and B are 0, then A plus B is 0. 0, 1, A plus B would be 1. 1, 0 is 1. 1, 1 is 1. Now we calculate F. F is A times A plus B and A plus B. F is A 0 times this one. So we are ANDing these two columns. 0, 0 would be 0. 0, 1 would be 0, 1, 1 would be 1, 1, 1 would be 1. If you look at f, f exactly is the same as a. When a is 0, f is 0. When a is 0, f is 0. When a is 1, f is 1. When a is 1, f is 1. So f is a. Okay. And we could do the same thing for this expression, a plus ab. These are two important expressions with absorption. The next one would be De Morgan's rules. De Morgan rules states that the nothing and or will result in and with elements negated. What does it mean? Let's see. A plus B. When you negate the whole thing, A plus B, when you negate the whole thing, De Morgan states that this will be A negated, B negated, but or will become and. These are the same as together. Again, I can write it for you as the different alternatives. Let me write it. A, B, and then I write A plus B. Then I write A plus B not or bar negated, and then I write A, B not. Okay. Again, A, B is 0, 0, 0, 1, 1, 0, 1, 1. A plus B is 0, 0 plus 1 is 1, 1 plus 0 is 1, 1 plus 1 is 1. And so not of this one, 0 becomes 1, 1 becomes 0, 1 becomes 0, 1 becomes 0. And now look at A bar and B bar. A bar, so let me write here A bar and B bar here. A bar, B bar. A bar is 1, 1, 0, 0, and B bar is 1, 0, 1, 0. So A bar and B bar, 1 and 1 is 1. 1 and 0 would be 0. 0 and 1 would be 0. 0 and 0 would be 0. Now look at these two columns. A plus B, the whole thing negated, inverted, bar, and the other one, A naught, B naught, and together. The same thing, 1, 1, 0, 0, 0, 0, 0, 0. So De Morgan states that complementing A plus B is ANDing A naught, B naught. And the same for the dual would be for ANDing. Negating and A dot B naught is A naught plus B naught. Dual. And becomes or becomes and. If you get something which is 1, always 1, it is tautology. If the output of a Boolean expression is always 1, is tautology. So if you get something 1, then you remember, when you OR it with something, the result would be 1 again. If you AND it with something, the result would be that something. 1 plus anything would be 1. 1 times anything would be that thing. And if the output of Boolean expression would be always 0, then it means that it is a fallacy. So if you OR it with something, then that would become the something. If you AND it with something, that the result would be 0. So let's do some kind of simplification. xy plus xy bar, xy prime. So how do I simplify this one? Xy plus xy plus. I use distributive property. So this is the same as x times y plus y prime. Do you agree? Xy plus xy prime, you get x, and then it becomes y plus y prime. And then we have talked about y plus y prime. Y plus y prime would be 1. So x and with 1 would be x. So you see xy plus xy prime was equal to x. The next one, for example, x plus y and with x plus y prime. Again, distributive property. You might not be familiar with that because we don't have this in arithmetic. So it becomes x plus, and we have y from here, we have y prime from here, and we have dot from here. So it becomes x plus y times y prime, y and y prime. So the result would be x plus 0, y and y prime is 0, so the result would be x. We used the terms that we have already talked about, so we are using that to get the result. The next one. Oh, this is the one that I just explained for you with table, so I don't do it. We talked about the absorption. X plus xy is x. X times x plus y is x. It is absorption. X times x plus y is. Again, in the logic operation or Boolean operations, if you don't put, you can remove a dot here. So it means that there is a dot here. There is an and here. X times x plus y. So it means x dot. Okay. This one, x plus y prime times or and y. So we use distributive property. It becomes x plus. Sorry, this is and. This is and. X and y plus x. Oh, no. I have to explain it some another way. Okay, and this one. Okay, these two. Okay, I put them for the competition. So you calculate this one, and I am making there. So the question is, how do you prove this? Number 5, x plus y prime times y, how it becomes xy. Okay, let me create it for you. The first two people. Discussions. Competition. Start a new thread. Question 5. 5. Post. Okay, reply to question 5. Again, this one, you are going to prove this one. Anybody? Let me see if anybody have answered. Okay, Fadi. Very good. How many people? Oh, Lana. E. Very good. So we can see if you are right. Fadi says why and why is it, how does it come with this one? No. We don't have y here. You have to just add them and then write that. You are right, but you didn't write it well. Again, the Lana, x plus y prime. Okay, I guess Lana, where is Lana? Lana, yeah? Lana, oh, okay, Lana. So she is writing x plus y prime times y. It becomes xy, so the distributive. Xy plus y prime y, and the y prime is 0, so it is xy. Very good. E. Where is E? Okay, so you didn't work together, huh? Okay. So y prime, what's the question? No, you should have started from this expression, x plus y prime times y. You didn't write that. I don't know where did it come from, this one. Yeah, you had to start from that expression. Ben, where is Ben? Ben. Okay, x plus y prime times y. It becomes xy plus, oh, very good. So Ben and Lana, they were the first two who wrote it completely. Fadi, yeah? Fadi, yeah? You are Fadi, yeah? Okay. But
I changed it before.
Before what?
Yeah, before you open it, I changed it.
But it goes maybe no. When I opened it, it was like that. So maybe if I open it now, you have changed it. No, it's still the same thing. If you change it, I guess it will go down because it will be a new post. Let me see. Here. Yeah, here. It's here. Okay, thank you very much. So let's go to the next thing. 12:38. So we had this one. Now that we saw Boolean algebra, what would be the application? Why are we reading these things? You know, because the logic system inside a computer, the digital systems, they are work with 0 and 1s, with these things, with gates, not, and, or. So we have to see them. It is used to perform the logical operations in digital computer. In digital computer, true represents by a high voltage, and 0, which is false, is represents by low voltage. So if you build a circuit, the output of a design would be, let's say, 5 volt, then it means that the result is 1. If the output would be 0 volt, then it means that the result is 0. The fundamental logic operators is and, or, and not. And we talked about the truth table of them. I showed table to you. Now I am saying that we call it truth table. Truth table means it represents the function, but it has all possible combinations of inputs at rows, and then it shows the output value for each row. So if we have n inputs, then we have 2 to the n rows. If we have 2 inputs, then we have 4 rows. If we have 3 inputs, then we have 8 rows that we have to calculate and express the output. And it is from 0 to 2 to the nth one. So I showed you, for example, let's say we have A, B, and then A and B. The truth table has 4 rows, 0, 0, 0, 1, 1, 0, 1, 1. It starts from number 0 to number 3, 0, 1, 2, 3. and the result with the 0, 0 is 0, 0, 1 is 0, 0, 0 is 1 is 0 is 0, and 1, 1 is 1. Example. Show the truth tables for this one. F is x prime plus yz. How many inputs do we have? 3. So how many rows should our table have? 8. 8. So let's put x, y, z are the inputs, and f would be output. Since f has yz plus something, before writing the final f, I write yz and then I write f. Okay. So x, y, z, they are inputs. We have 2 to the n possible combinations of x, y, z. 0, 0, 0. 0, 0, 1. 0, 1, 0. 0, 1, 1. 1, 0, 0. 1, 0, 1. 1, 1, 0. 1, 1, 1. 8 possible combinations of x, y, and z. Now, we are calculating yz. Yz is AND of y and z. 0, 0 is 0, 0, 1 is 0, 1, 0 is 0, 1, 1 is 1. 0, 0 is 0, 0, 1 is 0, 0, 1, 0 is 0, 1, 1 is 1. So this is yz. Now we have to, I could write a column with x prime. So I write it here, x prime. X prime is the nut of x. So when x is 0, it becomes 1. When x is 1, it becomes 0. Now, for calculating f, we have to OR this column with this column. These two columns should be ORed. So, var 1, 0. ORing 1, 0 is 1. Oh, I hope I could write it here because it what? Here, 1, 0 is 1, 0 is 1. Oh, too bad. I wish I wrote it somewhere. 1, 0 is 1. 1, 1. Again, 1, 0 is 1. 1, 1 is 1. 0, 0 is 0. 0, 0 is 0. 0, 0 is 0. 0, 1 is 1. So we have 5 1s, 3 zeros for this expression, for this statement. X prime plus yz. Okay. We could use truth table to show that two operations are the same. X times y plus z, xy plus xz. You write once a truth table for this operation, the left-hand side, and once for the right-hand side. And you see the columns are identical in all possible situations, possible alternatives. 8, we have 3, so it's 8. In all of the 8 rows, they are the same. So it means that they are the same. X times y plus z equals to xy plus xz, and also the other one, distributive property. Okay, we have time. And one, if they are, it is 1 if both of them are 1. When do we use that? This is the truth table. A, y, a and y. 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1. The only thing is that. Or we saw that. This is the truth table. We have seen that before. Now I'm saying that this is the truth table of OR. In OR we have 3, 1, 1, 0. In AND we have 3, 0, 1, 1. Not. So the truth table would be like that. 0 becomes 1, 1 becomes 0. If we want to implement this Boolean algebra in digital design, we use gates. and, or, and not are the basic gates. We will talk about gates now. These circuits perform Boolean operations, and they are called gates, logic gates. So the logic gate, first one. The first one, a gate is a digital circuit which operates on the inputs, and then they produce an output. And it will perform a function for us, either and, or, not, or complicated, complex functions. Gates are digital circuits because the input and output is digital, is only 0 and 1. And there are three basic gates, and, or, and not. These are the basic gates. We have more gates, we will talk about that, but they are basic ones. AND gate. The AND gate is, we have talked about this. The output is 1 whenever both of them are 1, and this is the symbol. AND is the symbol. OR gate. OR gate is, the symbol is here, you see it is like curved, and here is curved also. And the result is 1 whenever one of the inputs on 1. And if both of the inputs are 0, then the result would be 0. Not is like that. This is not. You put a circle and after the triangle. This is not. A becomes A not. If it is 0, then it is not. In our logic applications, we use AND when we want to make something happen at the same time. For example, you have an alarm. You want to set it when you want. So you put an input of alarm switch. When you turn the alarm switch on, then if the sensor works and it detects somebody passed, for example, the sensor, then you want to get alarm. Otherwise, if you didn't turn on the alarm, so you don't want to make alarm. If nobody has shown up, then you don't want to have alarm. If both of them happen at the same time, I mean, you turned on the alarm and somebody is coming, somebody is passing the sensor. At that time, we want the alarm to run. So we use AND. Sensor and switch, both together should be on to make this on. Otherwise, one of them is 0, then the alarm is not on. For example, OR. For OR, when you want something, either this one or that one happens, then you want it to work. For example, you have two doorbells, one at the front and the other one at the back. So either one is pressed, you want to be notified. You want to know that somebody is at door, either at the front door or at the back door. So the front door switch is here. The back door is here. You OR them together and you connect this one to the bell, to the ring. Then either one is pressed or both of them even pressed, then you get the bell, you get the ring. Otherwise, there is no ring. So this is a good application for OR. Not. For example, you want to have a heater, so when the temperature goes high, it turned off. And when it is low, then it works. So you put the temperature detector at the input, so when it goes higher than 20 degrees, it becomes 1. And then when it becomes 1, so it will produce 0, so it turns off the heater. So this is an example of using a NOT operation. Example. This one. F is x prime plus yz. Do we have time to discuss? No? Finished? Oh yeah, finished. So you do it yourself in the home. It's easy. Write x prime. Okay. So for Friday, we will continue this, but we go to the simplification of these expressions. Okay, have a good time.